Hello, everyone. Thanks for coming. Sorry for it taking me a little bit extra time to log on. Anybody have any questions before we get started? Hopefully, everybody can hear me. Yeah, it looks like the audio is working. All right, so I guess there's no questions. I just sent out an email to everyone regarding the first face-to-face test. I had a student that was trying to take a test in a different way, and I evidently, one, I miscommunicated with them, didn't get their messages, and that, of course, presented a problem. But the other thing is, my chair wants me to, or actually not my chair, but my dean wants me to see if there's a way I can actually administer the face-to-face test via proctoring through our testing center, but via Zoom as opposed to making students come to the campus. I'm not requiring anybody to come to campus. In fact, if you read my syllabus, you'll know that you can have those tests proctored a multitude of ways. Uh, and normally a lot of people will get, a local teacher or something like that to do it, but also there's services where you can pay for it. There's services where you can pay for it where they'll watch you online, all sorts of stuff like that. I think he's shooting for me being able to let you guys be proctored by a testing center via Zoom so that it wouldn't cost you. I am in communication with the testing center. I'm waiting to hear back from them. So that's what the email I just sent out was about. So if y'all were wondering what's going on, that's what's going on. If you haven't taken the face-to-face test yet, that doesn't mean you failed it. It was supposed to be done by sometime today, but I've now given you at least until Wednesday to get it done through whatever method you end up doing. And hopefully by sometime tonight or first thing tomorrow, I'll know whether or not the testing centers can proctor your tests via Zoom. If that's also the case, it might be something where I can possibly do it too. So if you end up having a problem where you can't get the testing center to proctor your Zoom at the time you need, it might be something that I could do. So if they let me, I mean, if they can do it, then I definitely will. If I can do it all by myself, I'm okay with doing that as well, except I can't do it as many times as a testing center could. So that's the only downside. So uh, let's go ahead and get started back on chapter five. I want to remind everybody, as I've said numerous times, but just in case someone missed it, the way that my lab and mastering works is when I create a course, it sort of does either puts no assignments anywhere or it puts them all somewhere, but it basically doesn't necessarily do anything remotely reasonable about the due dates. So when I first sign up with a homework assignment, they have a lot of chapters and they're all just assigned these sort of random dates. So remember, you should be paying attention to class and what chapters we're covering. Like I just told you, we should be working on chapter five right now. That means we haven't started chapter six at all. And actually, no, I did say, by the way, I did say chapter five, but what I meant was chapter six because we're in the gravity chapter now. So, chapter six at best could be due this coming Sunday, but chapter seven, no matter what it says, isn't due. Chapter eight's not due. Chapter nine's not due. Anything I haven't covered can't be due. So, if you see the due date or not, that does not mean you have to do it. So, I just want to remind everybody of that. Uh, also, want to remind everybody to go ahead and send me a text message if you end up having a problem contacting me via email and you don't get a response within one business day, I ask that you text me at that point. And you can, in principle, call me, but I have to have your actual phone number or else I'm not going to answer it. If you leave a voicemail, I should find it eventually. But the problem is, I get like six or seven calls a day, and they leave messages. I don't know why. They think I want some kind of loans, and some other ones think I want insurance for my car and all sorts of stuff. So, anyways, I will find that and that sort of thing. So I apologize if you had any problems. But now that I've said that, just want to get back into the Newton's law of gravity and specifically Kepler's laws of planetary motion, that sort of thing. And that was the last thing we covered. I worked a couple examples using Newton's laws of motion. And then I stated the three laws of Kepler just so you'd know what they are. And now I'm going to solve a few more examples. So the first one we're going to solve is not unlike the one in the book, which I think, let me see if I can even see what it was called. Yes, it was example 6.3. So in example 6.3, we basically had the Earth, the Moon, and the Sun. And in fact, the Moon made the vertex or the 90-degree vertex of a right triangle. The Earth made another vertex, and the Sun made a third vertex. And we're asked to compute the net gravitational force on the moon due to the sun and the earth. So that's what we're working on right now. I'm going to say example 1. Let me draw the picture I have in mind. I'm going to draw a moon right here. I'm going to draw a earth right here, and I'm going to draw a sun right here. Now, this is the moon. Oops. So this one's the moon, this one's the earth, and obviously this one's the sun. Now, what I know is the distance r between the moon and this is the logo we use for the sun. It's a circle with a dot in the middle. And that,
Are you
yes.
sharing your screen, Professor?
I was just sitting there thinking, oh yeah, I need to share my screen. And you answered and you piped in. Thanks, I appreciate that. Yep, completely forgot. Big old crackhead. Let's see here. Advanced. Yeah, there it goes. Thanks for correcting me on that. Whoever that was that Daniel that said that? All right. Now it should be coming up, hopefully. Look at that. You can even see the pictures. Sorry again. So, anyways, yes, the distance between the sun and the moon is essentially the same as the distance between the earth and the moon. So I'm just going to use that it is 1 astronomical unit, which equals 1.496 times 10 to the 11th meters. And of course, like I said, that's also the distance between the Earth, and this is the logo for the Earth, by the way, and the Sun is that one, the circle with a dot in it. We also have a distance between the Sun or the Earth and the Moon, and that would be the distance between the Moon and the Earth, which would be this guy. And that one's 3.84 times 10 to the, I think it's 3.84 times 10 to the eighth. Yes. 3.84 times 10 to the eighth. And that's actually in meters. It's 10 to the fifth in kilometers, but it's 10 to the eighth in meters. So we got that. Uh, Now I also need the mass of the Earth, the mass of the Sun, and the mass of the Moon. So we'll start off with the mass of the Earth. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the mass of the Sun is, I think that's 1.99, 1.99 times 10 to the 30th kilograms. So you can see that the mass of the sun is almost a full million times larger than the mass of the earth. And then finally, the mass of the moon, which would be m sub m. And in that case, the mass of the moon is 7.35 times 10 to the 22nd kilograms. You can see that the mass of the Earth is times 10 to the 24th, but it's 5.98 and this one's 7.35. So it's almost, but not quite, 100 times smaller in mass than the Earth is. So that gives you another idea, just in terms of everyday life, knowing how these masses are related. Now, what we want to do is we realize one, Newton's law of gravity says that F is equal to G m1 m2 over r squared, and G is equal to 6.67 times 10 to the negative 11th, and that's Newton's meters squared per kilogram squared. Okay. And Newton tells us that the law is an attractive force, so it defines a force acting on a body. Yeah. And in fact, it's a universal law of gravitation, as I told you, because it basically applies to any two objects that have a mass will experience a force of attraction to each other. And it also is a universal law because there's no R that you can put in that formula to get a zero for the force. So it literally reaches across the entire universe. Now, what we're going to do is we have to realize what directions are these forces, and that's another part that Newton gave us. He said the force of attraction acts along the line between the center of mass of the two masses. So what I'm going to imagine here is I'm going to imagine a z-axis and or excuse me, a x-axis and a y-axis. So let's say, for instance, this right here is going to be my y-axis. And let's say this right here is going to be my x-axis. And now I can draw the forces of attraction on the moon. So, for instance, the moon is attracted to the sun, so that force should be acting in the downward direction, like this. So, this is the force on the moon due to the sun, and it doesn't necessarily look exactly parallel to that line, but it should be. And then the force of attraction between the moon and the earth points this way, and this one's called the force on the moon due to the earth. So you subscript it moon and then earth. So our job here is to compute those two magnitudes and then use the magnitudes and directions to add the two forces. I think, hopefully, it should be fairly obvious to you that since these two forces are at 90 degrees from one another, then I'm not actually officially doing any quote unquote adding. It turns out that one is pointing in the y direction, one's pointing in the x direction. Therefore, the sum of the two is the Pythagorean theorem. And of course, you can use that to find the angle as well. So we'll go ahead and go about it that way. So let me go ahead and start with all this. This was our solution where I started writing down all those different facts, including, the actual equations we're going to use, so on and so forth. So now what I'm going to do is I'm going to calculate the force on the moon due to the Earth. That should be M, circle with a plus in it. And that's 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times the mass of the moon, which of course is 3.84, or excuse me, it's 7.35, my fault. 7.35 times 10 to the 22 kilograms. And then the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, like that. And then we're going to divide all of that by the square of the distance between them. And of course, the distance between the moon and the Earth is that 3.84 times 10 to the 8th meters, and of course we have to square that. So now you can see that the meters squared and the denominator cancels out with the meters squared in the numerator part of the units for the G. The kilogram squared cancels out with the denominators in the units of G. And we're ultimately left just with newtons. Sorry about my yawning. I don't know how I can stop it. So I'm going to go ahead and carry out this. You should be doing the same calculation just to make sure we get the same results. So I'm taking 6.67 times 10 to the negative 11th, multiplying that by 7.35 times 10 to the 22nd, and times 5.98 times 10 to the 24th. And then I'm dividing all that by 3.84 times 10 to the 8th, and that quantity is going to be squared. So I'm going to write in here squared, and now I can say the answer, and I get 1.988 times 10 to the 20th newtons. Now, we only had 3 sig figs, so the 8 and the 2 is not really a sig fig, but that's the magnitude of the force. Now I've got to do the magnitude of the other force, which is the force on the moon due to the sun. In that case, it's 6.67 times 10 to the negative 11th. This time I'm going to leave the units out because we've seen how they work out, and you guys should be able to do that in your heads. So 7.35 times 10 to the 22. And then the mass of the sun, which is 1.99 times 10 to the 30th. And then all of that divided by the one astronomical unit, which is 1.496 times 10 to the 11th meters squared. So now with this one, I'm going to say 6.67 times 10 to the negative 11th times 7.35 times 10 to the 22 times 5.98 times, excuse me, 1.99, not 5.98. So 1.99 times 10 to the 30th divided by 1.496 times 10 to the 11th. And now I'm going to square that. And that gives me 4.3592 times 10 to the 20th newtons. Again, we only had 3 sig figs, so the 9 and the 2 are not sig figs. But we can see that basically one is about as big as 2 and the other one's about 4.35. So really, if I wanted to make this a little more accurate, I would maybe extend the length of the moon sun force just a little bit bigger and maybe shorten up the other one. So this looks fairly decent. Now remember, when we add two vectors that are tail to tail, we complete the parallelogram. So completing the parallelogram, we can see that the net force should point right along here, like this, and I will find this angle as well as this magnitude, F total. Okay, so the F total, we can see that they're at 90 degrees angle with respect to each other. So we really just have to use the Pythagorean theorem. So I'm going to take 1.9882 and I'm going to square that, and I'm going to take 4.3592 and I'm going to square that. And outside of here, instead of writing equals, don't know why I wrote equals, I want to say times 10 to the 20th newtons, because you can imagine it would all come out that way anyways. So when I do this, I'll say 1.9882 squared plus, that gives me 3.95. That gives me 2 decimal places. And then when I do the 4.3592, when I square that one, I get 19.0. So that gives me to 1 decimal place. So now I'm going to add that to the 3.95293924. That gives me the square root of 22.9556 times 10 to the 20th newtons. And of course, now I can go ahead and work that out and say, raise that to the 0.5 power. And that gives me 4.7912 times 10 to the 20th newtons. That's how big the force is. And again, we only had 3 sig figs, so that 1 and 2 are not significant figures. So this is the magnitude of F total. And I can go ahead and box that off. And now I need that angle. And what we know is tangent theta. I use some old horse came a hopping through our alley. So tangent equals opposite over adjacent. So tangent phi is equal to the opposite. The opposite angle of phi is Fm sun, and the adjacent angle is Fm Earth. So that's the circle with the plus in it. So phi is going to be equal to the tangent inverse of. Now, again, we don't really actually have to do the 10 to the 20th. All I have to really do is write the 4.3592, and I don't even really have to write all that, but still, I'm going to go ahead and carry all those digits just because I did. So 4.3592 divided by the one for the Earth, which is 1.998, or excuse me, 9882. Sorry about that. Again, those last two digits, the 8 and the 2, are not sig figs either. So if I take the tangent inverse, so I hit shift tangent, and I say parentheses, 4.3592 divided by 1.9882, close parentheses, that gives me 65.483 degrees. Again, we only had three sig figs, so I'm going to say that's roughly 65.4 or 65.5 degrees, and that's our angle phi. Now, if you look at the book version, they did I think they even used the same numbers. They got 4.77 times 10 to the 20th as the force. That looks pretty close to what I got. I would have called it 4.79, but I carried more sig figs. And they also got an angle of 24.36, but their angle was this angle. So their angle should be my angle subtracted from 90. So if you took my 65 from 90, you get about 24 roughly, and that's what they're doing, 24.6. So this all matches. Anybody have any questions on that? All right. Your book does go on to talk about spherical shells, and that section is kind of important, especially for what's going to happen next semester. But basically, what the conclusion that's reached is let's go ahead and draw a circle or a sphere and imagine it as if it's the Earth. So I'm going to imagine a sphere that is 3 squares in radius, like so. And now I'm going to try to draw it and then let the software improve it. That looks pretty good. Okay, so we can imagine this as, for instance, the Earth or the Sun or the Moon or whatever. The main thing, though, is what Newton was able to show is by working with spherical shells, he realized that one, if you're inside of the planet, it's only the mass that's between the distance you are from the center of the sun or Earth, whatever you're in, only that mass between the center and the radius that you're at is really going to contribute to the force of gravity you feel. So let me explain what I mean by that. Let's say, for instance, I'm out here at 2/3 of the radius, as I've just drawn there. I'm going to put another dot here. I'm going to put another dot here and another dot here. And now I'm going to try to draw the circle, again, using the tools that the software provides to make good circles. Okay. So if you're out at that distance right there, and let's say that distance is, oops, let's take it off the automatic draw thing. That distance is R is equal to 2/3 big R, because of course big R is this distance. Okay. So if we're out at that distance, so here's a little person like me here standing here, the only forces of gravity that affect me are the forces of gravity that are between r equals 0 and r equals two-thirds r because I'm at two-thirds r. So if an object is at a distance of r equals two-thirds r from the center of the planet, then only the mass between r equals 0 and r equals two-thirds r will contribute to the gravitational force. Okay. So that's one of the big things we learned. Another thing we learned is it turns out that when you break these planets up into spherical shells, uh, it turns out that a single spherical shell behaves, at least as long as you're further away from the center of the planet than the shell is, it behaves just like all of the mass of the shell is at the center of the shell. So, in other words, when you have a spherically distributed chunk of mass, in other words, the all the masses, one way you can think of it is there's an equal amount of mass at radius, r equals two-thirds, and well, that's not really a good way of explaining it either. Well, let's do it this way. So you can say, for instance, let's show you I'm going to show you a shell, and this shell is going to be 1 square in radius, and then this other shell will be half a square in radius in principle. Okay, so that's supposed to be a spherical shell there. Now, what I'm saying is if you're out here in space and you're considering or concerned about the gravitational force that this ring of mass is applying to you, it turns out that this ring of mass will act exactly like it's a single particle of mass at the origin. So if this mass is m, then uh, the person cannot tell if the gravitational force due to the part of a planet is due to the shell or an equal amount of mass at the center, oops, of the shell. So what that means is whenever you have a spherically symmetric distribution of mass, it's going to behave, at least as long as you're outside of the mass, it's going to behave just like a single point particle at the center of that spherical shell. So as long as you're again not inside of the spherical shell, somewhere outside of the spherical shell, then the spherical shell gravitationally is going to act just like a point particle at the center of itself. And in fact, that point particle should have exactly the same mass as the spherical shell does. I wrote it as if he couldn't tell the difference, and that does the same thing, but you might not have thought about it that way. So that's two major things to learn about how gravity and what we call central forces behave. So central forces are forces that are symmetric about a single point, and that single point is the center of the spherical object in the case of gravity or the Coulomb force or the magnetic force. So that's a little bit about spherical shells. I just wanted to make sure you get that from the reading. I want to also go ahead and remind you that whenever you want to calculate, the total gravitational force on something, just like we did in this problem, we took the gravitational force due to one object, the Earth, say, and the gravitational force due to the other object, the Sun, say, and we then added them like vectors, and that's the way gravitational forces behave. They add like vectors, just like other forces do. We could, in principle, make a Newton's law of gravity that is a vector equation. And the way we do it is this. This is a vector form of Newton's gravity. Okay. So what you have to imagine is let's put a little coordinate system over here just so we'll have some sense of what we're talking about. This would be my x-axis, this would be my y-axis, this would be my z-axis. And then what we're going to do is we're going to imagine a little mass m1 here. And in fact, there's a vector r1 that locates the mass m1. Now, I'm going to go ahead and actually I drew it like a little kidney bean there, but I'm going to go ahead and treat it like it's a point particle. That would probably be a little cleaner and easier for you to understand. So let's do that. Forget about the idea of me drawing an actual kidney-shaped thingamabob. But we're going to say this is the mass M right here. That's the mass M1. Now I've got another mass M2 that might be, let's say, right here. This is the mass M2, and there will be a vector that points from the origin of that coordinate system to the center or to that point mass M2, and that vector will be called R2. Okay. Now, what we know is Newton's law of gravity told us that the force of attraction would act along the line connecting the centers of mass of the two particles. In this case, it's just particles, so there is no quote unquote center of mass because they're only infinitesimally large, anyways. But the main thing to get from that is this line from M1 to M2 or from M2 to M1. That's the line along which gravity acts. So this is the line along, oops, which gravity acts. In other words, the force will be parallel to that line in some sense. It might point from M1 to M2, it might point from M2 to M1, but that's all it can possibly point to. So now I'm going to work out exactly what it is. So for instance, if I want to talk about the force on object 1 due to object 2, okay, that's what F12 means. And what we know is it's got to be attractive. So in order for it to be attractive, we need the force to actually point from M1 towards M2. So that's the direction right there of F1, 2. Okay. Now, can anybody tell me whether that line F12, that little vector there, is that parallel to R1 plus R2? Is it parallel to R1 minus R2? Or is it parallel to R2 minus R1? That's the key to understanding all of this. Let me write that question down in case someone don't understand. Is the force F12 shown parallel to R1 plus R2 or parallel to R1 minus R2 or parallel to R2 minus R1. Can anybody answer that question for me? Just in case someone's chatting that, let me check my chat screen. I was just looking where I forgot to put that on there earlier. Put my iPad up. So everybody sees you've got a vector R1 plus R2, we've got a vector R1 minus R2, and we've got a vector R2 minus R1. I'm asking which one of these would be parallel to that little red F12 vector, and it does not seem like anyone has answered
Is it
me. Go ahead.
yeah.
Go ahead, Daniel. Uh-oh.
Oh, someone texted R1 minus R2, which was my thought as well.
Gotcha. Okay. It's pretty close. It's actually R2 minus R1. Remember, R2 minus R1 is technically defined to be R2 plus the negative of R1. So if you wrote the negative of R1, it would look like this. So it'd be the same vector as R1, except it's pointing the opposite direction. And now you can see the negative of R1, this little green dash thing that I'm showing you right here. That negative of R1 is head to tail with R2. And since they're head to tail, you know that you can just draw from the tail of the first to the head of the last. And that's what tells us it's R2 minus R1. But thank you for letting me know that someone else is doing it and for stepping up yourself. It's the answer is R2 minus R1, which is kind of a pain because you'd like the force F12 to have the same order 1, 2. So in order to do that, all I have to do is I can say F1, 2 is equal to negative G. Notice putting the negative in there makes it all better. M1, M2 over. Now the actual distance is that vector R2 minus R1. It's its magnitude. So I'm going to say R21 squared times R2 minus R1. But notice when I multiply by R2 minus R1, that increases the magnitude by a factor of R21 square to the first power, and we need the magnitude depend on the 1 over R squared value. So what I'm trying to show you here is that this R2 minus R1 is going to be defined as R2 1 vector. And this R2 1 down here is that magnitude. So all I have to do to make it work mathematically is I have to put a cube on it instead of a squared. And that's because, like I said, if you just had the G M1 M2 over R21 squared, that would give you the right magnitude. But as soon as I multiplied it by R2 minus R1, that gave me an extra factor of R21. So I had to compensate by adding an exponent of 3 at the bottom instead of an exponent of 2. So this is the actual vector version of Newton's law of gravity. And you can see by having that little negative there, pop, 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 pop. Force on 1 due to 2 is R2 minus R1, R2 1. Oh, I put that whole negative in there so I could write it the opposite way. And oh, that's what I was supposed to do. So everything worked except the whole reason I put the negative in there, I completely forgot about after I did it. And that's because I wanted it to have the same distance here. So what I'm going to do is say this is R12. So this is R1 minus R2, and this is R1 minus R2, and this is R12. So you can actually make it match the subscripts by just putting that negative in there. So that's why the negative's in there, because now you can see in reality we wanted this vector to point from M1 towards M2, but you see R1 minus R2 points the other way, so multiplying it by a negative symbol gives me exactly the right direction. Any questions on that? So, in some sense, John, by the way, and Daniel for that matter, you could actually say R1 minus R2 would have worked fine. Only in order to make it have the same subscripts, I'll put the negative in there. So hopefully that makes some sense to you folks. The good news is you won't. This will come in really handy later in the second semester of the course when we start doing Coulomb's law. We won't need it too much now, but if you had it now, you could do a lot more cool stuff with Newton's law of gravity. All right. What I'm going to do now is I will leave you to do the calculation of the acceleration due to gravity at the top of Mount Everest. You'll see that there's actually a extra credit problem in your module where you can calculate the gravitational acceleration at the top of Mount Everest. You can calculate the gravitational acceleration at the bottom of the Marianas Trench, and you can also compare the height from the top of Mount Everest if you're just measuring vertically, not horizontally too, but the height from the top of Mount Everest to the bottom of the Marianas Trench, and you compare that distance to the radius of the Earth, what you'll find out is that when you do the same thing for a basketball, specifically a cheap rubber basketball with the little rubber pimples on it. If you measure it from the top of a rubber pencil vertically down to the bottom of a groove, it turns out that that distance from the top of the pimple to the bottom of the groove is a larger fraction of the excuse me, yes, a larger fraction of the radius of the basketball than the Mount Everest to the Marianas Trenches. What I mean by that is specifically the Earth is a more perfect sphere than a basketball. Even if you're just taking into account the pimples and the geography. So the pimples and grooves on the basketball and the actual geography of the Earth do not make as big a difference on the sphere as do the pimples and grooves on a basketball. So that's kind of neat. But I'll leave all that to you. However, I did want to show you something kind of interesting. So, for instance, this will be example. Let's say this example 2. Uh, a person of mass m is on a scale at the North Pole. What is their apparent weight. And then part B, so we can make this A here. If the person is on the equator, what is their apparent weight? Now, this might not seem immediately obvious to you, but let me show you what I'm going to be talking about here. So I'm going to again try to draw a circle to represent the Earth. And I'm again trying to draw it fairly neatly. So I am going to now go around. So, oh yeah, that was great. I hate it when it doesn't draw properly. There you go. Okay, so there's the circle that represents the Earth. What we're going to do is imagine this as the equator, and up here would be the North Pole. And what we have is a little scale up here with a person standing on it. And then what I also have over here is a scale with a person standing on it, like so. And our job is to figure out exactly what the force the scale has to supply is. So if I take this one, what I get is a mass M, and I'm going to say that this is my y-axis. Nope, I'm going to say that downward is my positive y-axis, and I'm going to say leftward is my positive x-axis. Okay, so this one's going to have a mass m as well. Let's start with the North Pole one. So this is what I'm doing up here in the top right. The forces we have acting on it are the gravitational force, which we know is the object's weight. So right here, I have mg, but we also have a normal force supplied by the scale. And in fact, that's exactly what force the scale is going to read, assuming you had it set to a force as opposed to a mass. Now, this object is not really accelerating, the one on the North Pole. In fact, they're just rotating around in a circle like this. So they're not really accelerating unless you wanted to sort of count that the edges of their skin to the right or to the left is accelerating towards the center of their body, but that's pretty much it. Now, when we do the same thing for the object on the equator, it's going to come out different. But in this case, all we have to do now is say the summation of the forces in the y direction equals mass times acceleration in the y direction. There is no acceleration. The object is, in fact, not accelerating at all. And we end up getting mg minus the force that the scale has to supply is equal to 0. So we find that the force of the scale reads is just mg, which is our normal weight. So at the North Pole, no problem. It's just the normal weight. But when we try to look at it on the equator, things are a little different because in this case, we're going to have the weight pulling to the left. So that's my mg. And then we have the force of the scale, the normal force, is F sub S. And that, of course, points away from the center of the Earth. But in addition to all that, we realize that in order for the person to stay on the equator, they have to actually have an acceleration to the left as well. And that acceleration is the centripetal acceleration, which equals v squared over r. Okay, so we can now work with that and calculate what the new mass would be. So what I'm going to do is I'm going to work out the summation of the forces in the x direction equals mass times acceleration in the x direction. And notice I chose the x direction to point to the left specifically because I wanted it positive. So now what I have on the left-hand side of Newton's law is mg, because that points in the positive x direction, minus fs, because that points in the negative x direction, is equal to m times v squared over r. So we can actually solve for fs, and what we get is fs is equal to m times g minus v squared over r. So you can see that the weight is actually going to be a little bit less on the equator. Independent of you changing your diet or anything like that, it's just going to be a result of that because part of your mass is being used to cause yourself to accelerate towards the center of the earth so you can stay on the earth while it revolves around its center or rotates around its center. And then the rest of your mass, of course, is just going to count as your weight, but you get that free deduction because your weight is actually being used as part of the force to keep you in rotation. So now we can calculate what that quantity is. V is equal to 2 pi times the radius of the Earth divided by the period of the Earth's rotation. Now, technically, the period of the Earth's rotation should be around 23 hours, 56 minutes, but that's close enough to 24 hours for us. And we can go ahead and say 2 times pi times the radius of the Earth. And of course, the radius of the Earth is 6.38 times 10 to the sixth meters. I think that's what, am I remembering something else? Let's see. Yeah, I think that's the distance for the Earth's. Yes, 6.38 times 10 to the 6 meters. Okay, so that's the radius of the Earth. And then we're going to divide all that by 24 hours times 3,600 seconds per 24 hours, or excuse me, per 1 hour. So we can erase that 2 4 down there. Uh, and now we can see exactly what the speed of the Earth will be at the equator. So I say 2 times 3.14159 times 6.38 times 10 to the sixth. That's just the top part. Now I'm going to divide that by parentheses 24 times 3,600 in parentheses, and this gives me 463.97 meters per second. We really only had 3 sig figs, so these guys don't count. But just to give you an idea how fast that was, I can multiply this number by 2.237, which is converting it to miles per hour, and that's basically 1,037 or 1,038 miles per hour. So that's pretty darn fast, but that's just what the Earth rotates as a result of just being able to spin at 24 hours, every 24 hours. So now that I have that, I can say that AC is equal to V squared over R. So that's going to be 463.97 meters per second squared divided by 6.38 times 10 to the 6 meters. And 463.97 squared divided by 6.38 times 10 to the 6 gives me 0.0333741 meters per second. So it turns out that F sub S is equal to M times 9.80 meters per second minus 0.0333741 meters per second per second, which basically gives you really close to 9.77 G, or 9.77 in place of 9.80. So you can see once you actually do the calculation for the gravitational acceleration at the top of Mount Everest, that turns out to be right around 9.77. So the effect of being at the equator is about the same as the effect of being at the highest place on Earth. So, any questions on that? Notice the difference in the answer. If M was, let's say, take M equal to 100 kilograms, then force of the scale at the North Pole would be 100 times 9.8, so that'd be 980 newtons. But the force of the scale on the equator would be 100 times parentheses 9.8 minus 0.0337. In this case, woo, nitty. Oops, I did something wrong. Hold on a second. 100 times parentheses 9.8 minus 0.0337 close parentheses. That gave me 977 newtons. So it's not a huge difference, but it was a difference, as you can tell. Anybody have a question on that? All right. Now, your book does take a little bit of time and talk about weightlessness, so I want you to understand this. A common misconception, so pay attention to this part because what there's no way around this, but all the studies have shown is that when you actually state something to someone that's false and then you come back and correct it later, then they seem to only remember the original fact, which wasn't a fact and was in fact wrong. So I want to be careful with this, but this is not what's right. Okay, this is not what is the right thing. The right thing is that we are weightless in outer space. For instance, if you're in the International Space Station or you're in one of the SpaceX vehicles and you're actually in an orbit around the Earth, we are experiencing weightlessness there because we're in free fall. It's not because of there being no gravity. In fact, generally speaking, when we're in orbit, when any of our astronauts are in orbit around our Earth, they are never, ever, ever orbiting, or at least they haven't been orbiting farther away than the moon is. So you know they're closer to the Earth than the moon, and normally people will say, "Oh, it's they're weightless out there because there's no gravity in space." And they sort of mean, hopefully, they sort of mean the right thing, mainly that gravity got so weak that it went to zero out there, not that it just stopped at the border of the Earth. But even that other version's somewhat incorrect. It does actually decrease as you get farther and farther from the center of the Earth. But if it was actually zero out there, then there would be no chance for the actual moon to be tethered to the Earth. So we know for a fact that there's got to be gravity out there. So the effect that the astronauts are experiencing is more like the effect you get when you ride over a negative G hump on Apollo's chariot, or when you ride over a railroad track hump in a road while you're riding in your car, you'll feel that sort of butterfly stomach thing. That's you sort of in free fall. So what's going on is this weightlessness is what you experience when you're in free fall. So I just want to make sure you guys knew that as a general fact, because that's a common misconception that it's because there's no gravity in space or something weird like that. What I'd like to do now with this example is calculate the distance and velocity for a object in geosynchronous orbit. So we're going to call this example 3. At what altitude and speed must a satellite orbit to be in a geo. Now, your book is calling this geostationary. You're probably used to hearing it called geosynchronous. I'll accept both of them, of course, but I'll write down geostationary orbit. Now, what we mean by that is if you're in a geostationary orbit, then you're going to be directly above the Earth's equator. If you're, well, you have to be directly above the Earth's equator, and you're moving in your orbit at exactly the same speed as the surface of the Earth is, so that you always have exactly the same spot on Earth directly below you. That means, in general, your period of orbit should be exactly equal to the period of rotation for the Earth, which is 24 hours. So that's what we're shooting for here. So the way we solve for such issues is depends on whether we're solving for the distance or are we solving for the speed, and I'll show you how to do that. And this is actually the way you go about deriving Kepler's third law. The square of the period is proportional to the cube of the semi-major axis. So you'll see that as well. Basically, what we have is Newton's second law of motion, like that. We have Newton's law of gravity. Okay. And we have some information like T is the period is equal to 24 hours times 1 hour, and the bottom is 3,600 seconds. I think this is 14,400 if I remember correctly. Let's see. 24 times 3,600. 86,400. 24 times 3,600. Yes, 86,400. There it is. Seconds. So that's the period of our orbit. We don't necessarily need any masses right now, but we do need, for instance, the distance between them, and that's what we're trying to solve for. So R orbit is the question mark, and V is the question mark. Now, using Newton's second law, the only force acting on a satellite pretty much is the gravitational force. We're going to assume it has the appropriate speed and everything so that it can make the orbit, but the only force is the force of gravity. So the left-hand side of Newton's law becomes G times the mass of the Earth, which would be that one, divided by the radius of the orbit squared times the mass of the satellite, lowercase m. Well, this is the equation of motion, i.e., Newton's second law of motion for the satellite. So the m is the satellite's mass, and then the acceleration, of course, has to be the centripetal acceleration necessary to keep the object in a circle, and that's v squared over r. So if we wanted to solve for v squared, we could go ahead and eliminate r, but if we wanted to solve for r, we could go ahead and eliminate v. What we do know is that v has to be 2 pi times the radius of the orbit divided by the period. So I'm going to plug that in. And notice you can already divide through by lowercase m, and you can already divide through or multiply through by r, and that'll leave a lowercase r on the left. Now I've got G times the mass of the Earth divided by the radius of the geostationary orbit is equal to the square of the velocity is 4 pi squared r squared over t squared. So what we're looking for here is really the r, and what you can see now is g m t squared over 4 pi squared is equal to r cubed. So this is Kepler's third law. I just basically worked out Kepler's third law in some sense. You can treat it a little more generally by finding the center of mass of the system, but this is just assuming that the mass of, in this case, the Earth is monstrous compared to the mass of the Moon. So this is sufficient. But it does allow us to figure out what R is. So R is going to be the cube root of GM t squared over 4 pi squared. So R is equal to 6.67 times 10 to the negative 11th, leaving the units off, times the mass of the Earth, which is 5.98 times 10 to the 24th, and that would be kilograms, of course, times the square of the period, which is 86,400. Oops, I almost wrote it backwards. 86,400 squared. All that will be divided by 4 pi squared. And I'll get the cube root of 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 86,400 squared divided by, now I'll put it in parentheses and say 4 times 3.14159, and I'm going to square that 3.14159, and this gives me 7.5422 times 10 to the 22. All that's under there, and that has to be actually meters cubed. And if you work it out, you'll see that it is. Now we can take the cube root of that, and that means I'm going to raise it to the 0.33333333333 power, and that gives me 4.2250 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters. So that's markedly bigger than the radius of the Earth. And we were actually asked for the altitude. So the altitude of that satellite is actually equal to R minus the radius of the Earth. So it's going to be 4.22. Remember, the 5 and the 0 definitely are not sig figs. Times 10 to the 7th meters minus the radius of the Earth. And of course, the radius of the Earth is the 6,380 kilometers, which would be 6.380 times 10 to the 6th meters. And when you subtract those two, that's basically 42 million minus 6 million. So you can see that you're going to get pretty much around 38 million, 37 million, somewhere around there. So I'll say minus 6.38 times 10 to the 6, and that gives me 35.8705 times 10 to the 6 meters. So you can see that's on the order of 36 million meters, and the radius of the Earth is only about 6 million meters. So you're getting almost 6 Earth radii in altitude. So that's a really big difference. So that's the altitude. And we can say that it's on the order of 6 Earth radii. Now, we also want to know what the velocity is for this, and you'll find out that the velocity of this is actually quite small compared to, for instance, at 200-kilometer altitude. But what we have to do is just take that v is equal to 2 pi r over t. So we're saying 2 pi times 4.220 or 50, excuse me. 2250 times 10 to the 7th meters divided by 86,400 seconds. So that's 2 times 3.14159 times 4.2250 times 10 to the seventh, and then divide that by 86,400, and that gives me 3,072.5 meters per second, which only the first three are sig figs. If you did the same thing for a distance of 200 kilometers or an altitude of 200 kilometers, you'd find that the velocity there is like 8,000. So you can see the 3,000 is much smaller, but still, it's a pretty fast velocity. Anybody have any questions on that one? So yeah, if you want a geosynchronous orbit, which is like what you're using for your dish network or direct TV, they have to have a clear view of the southwestern sky. That's because we're on the East Coast, and they generally are in many cases. I've noticed uh, they've actually put the satellites somewhere in line, like in the same longitude as roughly the middle of Kansas. So if you put it at that longitude, but you put it up at 0 degrees latitude, that means it's right over the equator, but right over the equator part that's right directly below Kansas City, Kansas, or something like that. So we've got to look not only to the south, which is where the equator is, but we also have to look to the west because it's closer to being over top of Kansas than it is to being over top of Virginia or North Carolina. Any questions on that one? All right, we got only about 6 or 7 minutes left. Uh, I want to express to you Kepler's laws. So I've already told them to you once. So this is Kepler's first law, we'll call K1. And what it means is imagine you know you can put a nail in a piece of plywood, and then you can take a string, tie it to that nail, and then tie the other end to a pencil. And then if you hold the pencil up perfectly and keep the string nice and taut, you can use that to draw out an exact circle. What turns out that a more general version of that is to take two nails and stick them in a sheet of plywood, and then connect one end of a string, tie it to one nail, and then take the length of string, which has to be considerably longer than the distance between the two nails, and tie the other end to the other nail, and then poke your pencil in it and pull it taut. You get a whole different structure, and that whole different structure is this. So let's say this is my nail and this is my nail. It turns out that as I pull that string taut, it might be right here. So you can imagine the string goes up and then the string goes back down. But if I keep it taut, what should happen is we should get something like that. Now, that one's just me drawing it, so obviously it's not as good as if we actually did the experiment. But after the fact, I can totally make it look like it was a really good job. So I can do something like this, and then you'd see that in fact this distance is called the major axis. This distance, dead center between the two, is called the minor axis. And half of it is called the semi-major axis. Just like half of the other one will be called the semi-minor axis. Okay? Now, when you look at that, what Kepler's law says is that the sun will be at one focal point, let's say right here, and nothing of importance will be at the other one, but it's this shape, which is called an ellipse. And that's the actual shape of the orbits that the planets orbit in. So Kepler's first law is the planets orbit the sun in elliptical orbits with the sun at one focal point. K2 is that in the same sort of orbit, so let's see if I can draw it pretty well. I'm going to try to use the software to make it neater. I don't know if it'll do. Yeah, it does pretty good. Okay. Well, way better than I did. Let's put it that way. So there's your semi and your major axis. Let's imagine that your sun is right here. Now, it's weird, but you've got to imagine that the line connecting the sun to the center of the center of the sun to the earth at one point makes a line. So we can, for instance, consider a line from the center of the sun to the center of the earth. And let's say this occurs on day 0. And then over here, that occurs on day 30. What Kepler's second law says is the planets sweep out equal areas in equal time. So whatever the area is in this sort of pizza slice, if we find two other points that are separated by 30 days, then they too will have the same size pizza slice or the same area in it. So you can imagine, since this pizza slice is so long, it has to be super thin. And you might say this would be day 0 and then this would be day 30. If that's the case, then lo and behold, you'd be right. The areas are equal. Now, as I said, Kepler's third law was the square of the period is proportional to the cube of the semi-major axis. Well, the semi-major axis is A, and what I want you to realize is this distance from here to here is A, and this distance from here to here is A. So the whole thing is 2A. This distance from here to here is actually the smallest distance between the planet and the star. And this one here and here, that's the largest distance between the sun and the planet. Okay? So it turns out if you add R plus R, I think you can see you get 2A. So if you take the average of R plus R, there's only two measurements, so you would want to divide that by 2. Well, since that's also equal to 2A, that's the same thing as dividing by 2 over there as well. So you see that the semi-major axis A is actually equal to the average radius in the sense that it's the biggest plus the smallest divided by 2. Any questions on that one? All right, so it looks like we're going to be doing a little bit more of this next time. You guys are free to go. Uh, Wednesday, remember, is the last day to get your test finished. It was Monday. If you already finished it, I send out an email. You're allowed to actually take another poke at it if you want to. You don't have to, but I will let you since I'm giving other people another couple of days possibly. So anybody that wants to take it, you just have to choose whether you're going to take it now and take the second score no matter what. It's not going to be. I can't give you the idea of I'll give you the higher of the two. That's not fair. But you can still take the other one if you think you do better by having 2 more days of study. You just need to let me know, and then you got to set up a proctoring setup. So keep an eye out on your emails. I will let you know as soon as I do. But have a good evening and thank you for coming, everybody.
Have a good night, Professor.
You too, Aruz. All right. That looks like it. Okay, so that was that. And that's that. Have a good one, everybody. Bye bye.